Afternoon, everyone.
Afternoon, sir.
How you doing?
We are fine, thanks. How are you, sir?
I'm all right. Who can tell me what is this? It's a symbol, ne?
Yes, sir.
What symbol is this?
We don't know, sir.
You don't know. It looks like what? It reminds you of what?
Resistor.
A resistor, ne?
Yes, sir.
But it is not a resistor, ne? A resistor is sharp on the edges, ne? So that does it look like. This is an inductor, ne? You don't know an inductor. An inductor looks something like this, ne? Looks something like this, ne? It's basically it's just a coil of wire. They coil it on something, ne? They call that thing a ferrite magnet material, ne? And this one as well. Inductor basically is made from a piece of wire like this one, ne? Then when they coil it onto something, and then it becomes an inductor. Before they coil it, it is called a conductor, ne? Once they coil it, it becomes an inductor. This one is an echo. I did it myself, ne? But now it's an inductor. What makes an inductor different from a resistor besides the symbol? Yes?
The symbol of resistor is sharp, like...
No, besides the symbol, the functions. Why is the inductor different from a resistor? It's the function, ne? A resistor, we said it limits the current, ne?
Yes, sir.
And it divides the voltage. But an inductor, okay, let me draw the 3D one. Something like this, ne? There's the echo one. Let us just show you now. Now on the inductor, let's say you supply this inductor with 12 volt AC, ne? And then you ground this side. If you supply it with a 12 volt, just like this, it will generate, what is this? Magnetic field, ne? Around this coil there will be a magnetic field. And it have a direction. To be able to determine the direction of the magnetic field, you use your right hand, ne? Like sharp, ne? So if the current, your thumb must face the direction of the current, ne? And the four fingers will tell you the direction of the magnetic field. It's in a form of a rotation, ne? So let's say now it's like this now. They say in a wire, if you supply it to 12 volt, let's say AC, here we ground it. Just like that. In a wire carrying current, there will be current must running through this wire going up. So you say sure, ne? If you say sure, it means the current is going up. So the direction of the magnetic field will be in this direction, ne? Can everyone see that? There will be a magnetic field around this wire. So now in an inductor, once you loop this wire, there will be more magnetic field, or there will be greater magnetic field that is generated, ne? So as the reason why I wrote AC here is that this current that flows here is not direct current like we've been talking about in the past class, ne? This one is alternating. You saw this alternating current in the oscilloscope last time, ne? So when this current, it must flow first in the positive direction, then it come back on the negative direction, and first in the negative direction and come back in the positive direction, ne? So as it flows back to this zero line, it means now it's changing direction. This is positive and this is negative. What happens in a magnetic field around the coil is that it collapses and expands. collapses and expands. So as it collapses and expands, it induces its own current back to this coil. Let's assume here that the current flows in this direction. Now the current induced by the magnetic field will oppose the very same current that generated the magnetic field. So basically the inductor doesn't like the change in current. So when the current rises, the inductor forces it to drop. When the current starts dropping, the inductor forces it to rise. It only likes a steady current. Now do you understand now? But now, what do we use an inductor for? The question still stands. The first answer is there on the board already, to generate the magnetic field. If you want to generate a magnetic field, you already have an inductor. Besides that, what do you need an inductor for? We use it to filter noise. That's why you see a lot of them in the computer power supply. We use it to filter noise. We use it for tuning. In that radio that you listen to, the Ukozi FM. What else? What another radio station that you listen to? Metro FM. All those radio stations. Somewhere they use an inductor for tuning. You also use it in a tuning circuit. Where else do you use an inductor?
Stove?
Yes. No, but not like that. There are new stuff that they use. They call it. It have a coil, mostly. That coil is part of induction. They call it an induction heater. That type of stove. Yes, you are right. See, you are observant. They call that stove an induction heater. So now, how do we determine the value of an inductor? How do we know? You can use this piece of expensive equipment to measure the value of an inductor. But there was a formula, there's still a formula that is used today. It's called the inductance is equal to permeability. Remember I told you most about the echo one. The other one used the ferromagnetic material. That's where you get this value from. The echo is 4 pi multiplied by 10 to the power minus 7 Henry per meter. What is Henry? Henry is the unit for an inductor. What are the unit for a resistor?
Ohms.
Ohms. Capacitor? Farad. And then we multiply by the number of turns, but to square the number of turns. You also multiply by an area, the size of your inductor, then you divide by the length. Then you can approximately determine the value of the inductance. The L represents an inductor, permeability, number of turns, you must wind it, number of turns, and then the area, the total area of the inductor divided by the length, how long is it. But other inductors, they come with, especially the SMD inductors, surface mount device inductors. They look something like this. Let me check on my table. They look something like this. This is the SMD one. Can you see it? Can you see it? You can have it. I have more here. There's SMD inductor. Now the SMD inductor, they come with numbers. The right numbers there depicted. You see a number? Can you see a number there at the back? What is the number there?
188.
100. I want to start afresh and show you what represents what you should know by now. We did it in a resistor, we did it in a capacitor. You should know by now in an inductor. You know, this is a digit, so it's a 1. There's another digit, there's a 0, so there's nothing. Micro who? Micro Henry. So that one is 10 microhenry. Another number?
M88.
No. The number, read there. What did they write there? 681. They wrote 681. So what is the value of that inductance of that inductor? It's 6, 8. Since there's a 1, that means there's a 10 microhenry. You must practice, ne? It is the same. It is the same. You read the numbers the same way for surface mount, resistor, surface mount, capacitor, surface mount, inductor. The calculation is the same. Ne? You must just practice, ne? Practice, practice, practice. Now we're going to make our own inductor. I'll show you. Borrow me that thing is there. That's how you're going to make our own inductor, ne? The wire must face you, ne? And then pinch it with your thumb, ne? Then start rolling. What am I making here? An inductor, ne? The coil. You also call it a coil, ne? Was it difficult? Nope, not at all, ne? Those who are going to make a toroidal inductor, if it's circle like this, they call it a toroidal inductor, ne? Mostly it's used in audio circuits, ne? You're gonna put it in like this. Can you see? And then you insert your wire. Don't let the wires twist, ne? It must be one uniform coil, ne? Make sure that your hand is strong, ne? Then you pull. Easy. Look at that. Can you see? Let's get going. How is it going? Okay. Let's see. How do you feel that you made an inductor today?
Happy?
Feel happy? Let's see if it's an inductor. Yep. 0.07 millihenry. You see the Henry is even there in the meter.
Yes, sir.
Yeah. Now let's check the next one. Your inductor looks ugly, but it's fine. It's your first time, yeah? 0.01 millihenry. That's good. Let's move to the next one. How do you feel you made an inductor today?
Fine.
You feel awesome. What are you going to do with this inductor? Don't know. I told him what's the uses of an inductor. Okay kids, now I want to demonstrate to you the magnetic field around the inductor. Do you know what is this? That black thing on the table?
Compass.
It's a compass. Yes. Do you see that red arrow?
Yes, sir.
Look what happens when I bring the inductor closer. Do you see anything?
No, sir.
No, stand still. Let's see what will happen as soon as I put the inductor over that arrow. Over the compass, I mean. Can you see?
Yes,
Do you see the red arrow?
yes, sir.
What happened?
It moved.
See. Can you see?
Yes, sir.
Did I touch the arrow?
No, sir.
What causes it to move?
A magnet.
It's a magnetic field.
Yes, sir.
Let us swap the direction of the magnetic field. The direction of the flow of current and see what if the arrow gonna change the direction. Can you see?
Yes, sir.
Now observe. Did you see? As soon as I change the polarity or the flow of current, the direction of the flow of current, the arrow also changes direction. That indicate the magnetic field around the inductor.
Yes.
Did you see that?
Yes, sir.
Yes. Now let's see the behavior of the compass when I use the real magnet. Look, I don't even have to bring it close. It also flip because this one is the real magnet. So I did prove that the inductor carrying current have a magnetic field around it. And we're back. Did you see that when we 12 volt AC, when we change the direction of the flow of current, the magnetic field around the coil change? You saw almost by means of the, what is that, the compass?
Yes, sir.
Yes. So what we did was, at first I plugged in the ground, then I touched the 12 volt wire. So let's say now, let's assume that the current was flowing up. So the magnetic field was flowing in this direction. You saw the compass rotating. I then attached the ground, and then attached the other hand with the 12 volt AC. So the current was now flowing the opposite direction. You still use the same hand, but now where's the current flowing? In which direction is the current flowing? Down. So you do it like this mostly. So the direction of the flow of current also changes. Did you see that?
Yes, sir.
It was easy. But now the opposite also happens. We say if we induce current in a wire, it generates magnetic field. What happens if you put a magnet closer to the coil? What will happen? The opposite will happen. It will generate current. That's when the magnetic field are used, the inductors are used as a sensor to sense the magnetic field in the atmosphere. That's how your radio operates. They use most an antenna. So the antenna will sense the magnetic field that is sent by the radio. Then the radio, that magnetic field carries information mostly. Whatever music that is playing or the news, it will then be trapped in this wire, or it will then be absorbed by this wire in a form of current. And then it will go to your radio via the antenna, and then you're gonna hear the DJ. That's how the radio that's how the radio works.
Yes, sir.
Yeah. So now let's compare the three what do we call these components again?
Resistor. Inductor.
They are passive
Component.
electronics components. Let's start with the resistor.
Yes, sir.
Resistor. The symbol of a resistor looks something like this, with the sharp edges. And then an inductor. Another name for the inductor is a coil. Some countries they call it a choke. And a capacitor. All these are passive electronics components. This is the symbol of a capacitor. What is the synonym for the resistor?
Ohms.
Ohms. We write it like this. Ohms. And then it looks something like this. The synonym for the inductor?
Henry.
Henry. But normally the unit you write them in microhenry or millihenry, as you saw on that meter. The synonym for the capacitor?
Farad.
You're learning. Farad, but normally it comes in microfarad. Now, if we induce or if we supply each of these components with a direct current voltage, VDC, what will the resistor do to the current or the voltage? The resistor only resists the flow of current.
Yes.
It only resists the flow of current, but it doesn't change the state of current. It doesn't have a problem whether it's a direct current or the alternating current. If we induce the direct current here, what does the inductor do? Store charge? No. Only direct current doesn't store charge. It just let the direct current flow. Actually, if you supply it with a direct current, it behaves like a resistor, more or less like a resistor. So if you supply it with direct current, it acts as a resistor. And the capacitor,
Store charge.
it blocks.
Start time. Delay time.
No, we'll get to that one. It blocks direct current. If you supply it with the alternating current, this one it just behaves the same as a direct current. It just resists. That's why they call it a resistor. Nothing much. If you supply the alternating current, what does it do? It generates a magnetic field. Basically, it opposes the rise of current, the change of current. So this one have a problem with current, but it doesn't affect voltage that much. So it only affects alternating current, but voltage not that much. Actually, it doesn't affect voltage at all. So I'm just going to put a tick here to say it doesn't have a problem with voltage. So if we were to connect all these components together as a RLC circuit, this inductor was going to delay the current with the X amount of time. That's what I'm trying to get you to understand. Not the voltage, the current. There's a difference between the two. Not the voltage, but the current. That's why I'm saying it affects the alternating current, but it doesn't affect voltage that much. So it let the voltage pass, but it affects the change of current. And then the capacitor. The capacitor doesn't affect the alternating current. Alternating current, it just passes. What about the voltage? You said it was earlier.
Store charge.
A store charge, but what about the voltage? It delays the voltage for a while. You said it earlier, Mos. So it have a problem with the voltage, delays voltage. So I heard you saying this, they store charge. Does the inductor store charge as well? Yes, it does. In a form of magnetic field. Yes, I told you earlier. It stores charge in a form of magnetic field only for a short period of time. Ne? Only it stores charge that will only last as long as there's current flow through the inductor. Ne? As soon as the current flow cut, that form of energy will collapse. Ne? How long will it take to collapse is determined by the amount of current and the value of the inductor. Ne? And the value of the inductor and the size of the magnetic field around the inductor. Ne? Yes. What about the capacitor? It stores charge for a very long time, ne? Even for months. That's why you need to be careful if you touch a capacitor. Ne? So now you see now how these guys differ from one another. Ne? So next time we meet, we're gonna build a circuit. We're gonna now put them all together in one circuit and see how is the current and the voltage is going to behave. Ne? Because we said this one affects the alternating current, but it doesn't have a problem with the voltage. This one affects the voltage, but it doesn't have a problem with the alternating current. This guy only resists. That's all it does. It doesn't affect no one, have a problem with no one. Ne? Ne?
Yes, sir.
Let me just here resist current. Ne? But it divides voltage, ne? Depending on how the circuit is connected. Ne? Only divide when the circuit is what? Is connected in what? In series. When the circuit is in series, you forgot. The current will stay the same, but you divide the voltage. Ne? We're going to have V1 and V2. Are you ready to build this circuit? So let me just show you how an RLC circuit looks like. Ne? This is my resistor, this is my inductor, this is my voltage. Ne? This is a snake. Ne? What does a snake represent? What does a snake represent? The snake represents the alternating current. Ne?
Yes, sir.
And then this guy is a battery. But what kind of current? It's direct, meaning it only flows in one direction. Ne? In our class, we assume that it only flows from the positive to the negative. Ne?
Yes.
Yes, but if you attend another class and then they tell you otherwise, don't be surprised. Ne?
Yes, sir.
Yes. So now, based on the knowledge we gained so far, if now an alternating current flows in this direction, what will happen as soon as the current gets here? A small amount will be resisted. Ne? Just a small amount, but it will also allow the current to continue to pass. Ne? Then what will happen as soon as the current gets to the inductor? It will generate a magnetic field. Ne? Around this coil. We learned it today, mostly.
Yes, sir.
What surprises you now? And then, but still, a certain amount of current is still going to pass, ne? Because it doesn't block the current, but it just delays it. Ne? Then as soon as the current passes and gets to the capacitor, what's going to happen? The capacitor plate will start charging. Ne? So it will delay voltage with a certain amount of time. So what will happen between these two guys is that they're going to start passing voltage to one another, because this capacitor charges and also discharges, charges and discharges. This one does the same. So the inductor will charge first and give the charge to the capacitor, and the capacitor will also charge and give some of the charge back to the inductor, just like that. Ne? We call that oscillation. We are advancing now. Ne? We call it oscillation. Ne?
Yes, sir.
But there's still gonna be a continuation of the flow of current. Ne? But you will see something like this on the oscilloscope. That's oscillation. Ne? If you remove one of these guys or remove both of them, it will be like this, like ain't nothing happened. Ne? And then after we build it and see it, then you're gonna apply it in real life. We see what project you're going to build. Ne? The class is adjourned. Until next time.